Hello, and welcome to the Give Your PXE Wings SREcon 2020 talk. And we're going to be talking about how this is not magic. It's how booting actually works. There's a ton of deep content. We're going to start with the basics and go super deep. And I'm your host, Rob Hirschfeld, co-founder of RackN. And we created a project called Digital Rebar, which is all about bare metal provisioning and then a whole bunch more. And this talk is actually a reflection of a hour-long discussion on the latest Shiny, which you can find on the PXE Wings. This is our bare metal mascot. We do a ton of things with bare metal, and we really care deeply about this topic. So I hope you'll enjoy this deep dive into provisioning. In concept, provisioning should be really, really simple. We're just installing an operating system on a server, right? Why should that be so hard? But the reality is that there's actually a lot of things we have to do and do just right to make this work, right? It's bootstrapping. We have to worry about just the fact that we are bootstrapping, right? Lifting a system up by its bootstraps is really actually impossible. So that's a challenge in itself. There's firmware limitations. There's variation between the platforms, makes it super hard, and the way they implement protocols. Networking is networking, and security, making sure that's all right. Getting the performance of the systems tuned and right is important too if you're provisioning thousands of machines or wanting to turn them over quickly. And then post-configuration, the whole configuration management space is in itself a major thing. And that's not even anything beyond provisioning. Provisioning doesn't even include things like getting system inventories and validating that it's correct and you can proceed and go correctly. Getting the system's hardware configured, addressing and naming the machines and injecting their credentials. These aren't topics I'm even going to touch, and they are critical to making provisioning work correctly. So what are we going to talk about? We're going to be exploring a lot of provisioning. We're going to be talking about net booting, which people know as PXE, but has a whole bunch of different names into it. We are going to be going through image deployment and some alternatives to NetBoot. And then we're going to be talking about some esoteric flavors about how we provision and advanced topics for you. So hang on, even if we start with the basics, we're going to get to some really interesting advanced topics. But at the end of the day, all these roads are going to lead to the same thing, which is a kernel init process. It doesn't matter if you're Windows, VMware, Linux, something else, all of these processes are going to go through and ultimately load a kernel. And that's what we're trying to get to. This is RackN. This is one of many slides and charts that we use to explain how all this process works as part of our documentation. It's an eye chart. We're not going to go here. We're going to start a little more basic. And I'm not going to go even here, which is our skinny down version of all of the provisioning steps that you need to get through. So this can get very complex. And I only have 40 minutes. So let's start with something really simple. And that is just PXE booting something. So I have a video of a machine here going through a PXE boot process. And you'll notice it goes through a DHCP process. Then we're going to go through and download PXE Linux. We're going to talk about all this stuff. We're installing an OS. And this is going through and booting a system. We're going to break this down a little bit more and show you what it is. But at the end of the day, this is what it would look like if you were doing it using something like Digital Rebar. So pretty straightforward process, tons of script and dump and things that you can go through and look at and watch what's happening. And there it's completed an OS boot cycle. So let's explore what happened in that process. Basically, the thing that isn't clear, because it all flows together in the video, is that bootstrapping is a multi-stage process. The first thing that we have to do is actually get on the network, right? PXE booting is really about network booting. And so the firmware that is the PXE system, and remember, it's important to know, PXE is embedded firmware. It's on your NIC driver, and not all systems have it. Not all systems implement it the same way. But what happens is that little bit of firmware, if it's enabled in your BIOS, will start a system where it DHCPs to get onto the network. DHCP gets your IP address, and then DHCP has a protocol, it's UDP based, where it can get additional information when it boots, not just an IP address. It'll get where the gateways are, the name servers. It gets something called next server in the PXE format, and that is what you really have to set. Sometimes there's additional options that you need to make all this stuff work. But that next server instruction is what triggers the next step. So that tells it where to download the bootloader that it's going to use, which is traditionally, in most of our systems, would be an LPXE Linux 0 image. It TFTPs that image and downloads it. Now we're talking about firmware. Firmware is very small, very fragile, does not change easily, because once it's on that system, it's in the system. So TFTP is a lightweight version of FTP that uses UDP to get those transfers. It's slow, it can be fragile, right? It doesn't have any of the protections of TCP sockets built into it. It downloads that binary. And technically, you could keep using TFTP. Historic systems did, and they would download even more than what we're going to do. That's not what we do. It's not what industry practice has evolved to. We use a two-stage bootloader. So we get the smallest possible bootloader out of that TFTP transaction, and then switch to using iPXE, which is the modern version of those bootloaders. iPXE, which is often embedded in the BIOS for systems, you then download that. That can be downloaded over HTTP, and now we're going much, much faster. We can use secure protocols. We can get things transferred better. The sooner we get to this stage of the bootloader, the better. You'll actually notice that if you scroll back through that sledgehammer boot that I showed you, it's going to go stage 1 and then quickly transition to stage 2 from a boot perspective. Once we've installed that bootloader, then we can actually start getting the kernel for a real operating system. And this is where you're actually doing the operating system install, or building up enough operating system that you can start making real provisioning happening. So each one of these stages is actually a totally new operating system. And if you were watching a DHCP server, so Digital Rebar has an embedded digital DHCP server, and you can actually watch the events come in as you go through each one of these stages. It has to register a new, it doesn't change IP addresses if you've done it correctly, but it'll come through and build through each one of those stages. And it's literally 4 different operating systems that are being started to complete this process. People tend to think of it as one thing, but it's not. It's using 3 or 4 different protocols. It's using completely different operating system loaders. There's a lot going on behind the scenes to make even this simple process work. And I mentioned this before. In modern firmware, especially UEFI firmware, we can skip this initial PXE. We can jump right to iPXE, and most of the time that's what we see happening. It's what we do. We want to get out of that TFTP boot and UDP as fast as we possibly can. And so if we can, we'll just skip right over that step, detect that we can, and then move on and drop that one step out. And that can make a tremendous difference in the process. Before we were doing 2-stage bootloaders, a lot of times we had to download the whole bootloader in TFTP. And that would actually make it take 3 or 4 times longer because of the way the systems had to boot. And it's fragile firmware. So these things can be very sensitive about DHCP reservations, DHCP exhaustion. So lots of things that can go wrong in this. And so now we're done, right? We've got our system up and everything's provisioned. Well, I wish it was quite that simple. If I went back to my video here and jumped forward into what it would look like to netboot, say something like a CentOS OS. In this case, I'm going to see the same starting point. So this is the CentOS install, very similar thing. iPXE, DHCP, downloads the bootloaders. But in this case, I'm going to go into the CentOS bootloader, and that's bringing in the initRD image with this. It's not as optimized, so it's going to download more things using that second bootloader. And then it starts a traditional OS install, which is additional steps past getting that initial kernel on the box. And with the magic of time-lapse, I actually can compress this process, which takes quite a while, into just a couple of seconds. So why does this take so long? So we have to know that provisioning is much more than just getting PXE going. there's actually a lot of things that have to happen after we get that first kernel going. So the first thing that we actually have to do is kickstart. And there's other things, pre-seed, Weasel, different operating systems, but I'm going to use kickstart more generically. Because each server is different, every system is different, we actually have to guide what's going on. The kickstart is going to describe the inputs, the outputs, the drive configurations, network configurations. It's a lot. Those things are guided by templates that get injected into kickstart. I'm going to show those to you in a minute. Then we actually have to do installation of packages because the OS images that are distributed don't include all the packages and repos. So it's going to connect to the internet and download additional packages, try to go to the internet and download those from some repo mirrors. That process alone is a significant amount of time, not just the downloading, but actually going through and installing those packages and making them work. And then even after you've gotten all that going and your OS looks like a pristine system, that's not sufficient because you actually post-configuration. You have to get access, SSH keys, and user accounts. You have to get the systems named correctly. You have to start installing your application so the operating system could do something useful. That's a lot of steps that have to be done after you've gotten the most basics running. So this is really not just about PXE. When we're talking about automating provisioning, it means that we've connected all of these steps together. Now, in a lot of cases in the industry, we will say, hey, I'm PXE booting a system, and we'll mean provisioning it all the way through all these steps. And so you really don't want to just think, I've gotten my bootloader going and I've started Kickstart. To really think about what you're doing with this, we're actually building a complete end-to-end system. And that's where I'm going to focus both on some of these options for how you get this process started and going, but also how you look at it as an overall system. And that's because there's a lot more to consider for this. One of them is out-of-band management. What we just described is a process that goes through iPXE, which is a network boot, but that doesn't account for any out-of-band management, power on, power off, power reset, configuration if you want to do it through that model. And it certainly doesn't touch on infrastructure as code. This is such an important part of your process. And so many times we see people in industry who've just dropped a whole bunch of configuration files, or they have some standard templates in their cobbler server. It's an old bootloader. They haven't thought about how they're actually going to build this as infrastructure as code and influence that process. And I really want to stress how important this is. And it's not that hard to make this about infrastructure as code because, frankly, it's all software. So let's talk about some of these templates. I'm going to show you what they look like. This screen is the digital rebar code repository. So we have open source community content for all of the standard provisioners. And actually we open source a ton of edge and specialty provisioners also. In this case, I'm just looking at the CentOS 8 install. And if you look at what we consider a boot environments, it's all of these pieces put together in a single reference. And so that includes where you would get the ISOs. It includes all the templates that would be used to do that provisioning. Everything from where the PXE Linux, iPXE comes from, the grub components, secure components for those. And then down here is the Kickstart, the places where you would actually see those things go. I'm going to walk you through a couple of these pieces. This isn't the focus of the talk. Go check out Digital Rebar if you want to see more, but I do want you to see how this can be done as infrastructure as code. So when you're talking about iPXE, there are instructions based in iPXE that tell you where to go next. And so in this case, it's saying load the kernel, download the kernel from this location, and here's your boot parameters. And for this, it's parameterized so that if you know something about the system, you can influence what those are, then start this init-rd, which actually starts the kernel going. And then from that perspective, you can start doing things like installing better options. So we have a Kickstart pre-seed combination that actually is OS dependent and chooses different things. In this case, we would choose a CentOS 8 deployment. That's the one I showed you. And here you can see what I was talking about. It's setting things like time zones, keyboards. It's setting your root password, turning off SE Linux if that's your desired, setting up boot partitions and actually attaching all of the components into your operating system. It's actually doing a reboot using kexec, which we'll talk about in a minute, downloading all those packages I was talking about and going and getting them, letting you choose if you want to get them locally or if you're going to go back to the internet, and then ultimately handing off into post-configuration steps so that you can actually make all this stuff work. There is a lot of complexity in these scripts. This is why it's hard. And it's actually important to understand that when you go through this process, somebody is thinking through all of these steps to make this provisioning operation work. It doesn't just happen by itself. This is why hardware, frankly, is harder. So now that I've shown you those pieces, let's take a breath and answer some questions. We get a ton of questions about PXE and things like, and how it operates. Some of our frequently asked questions are, just straight out of the box. Why is this so fragile? Why is it so hard? I hope I've explained that. There's a lot of information you need to know about the systems to make it work. It's using a lot of protocols with a lot of handoffs. And you're relying on firmware to get this right. And the faster you get out of that process, the faster you can get to something more resilient. A lot of people ask about PXE over Wi-Fi. Wi-Fi requires you to have credentials. And so it's very hard to inject those credentials and then start the PXE process because PXE is starting before you've touched the machine at all. So we don't see a lot of PXE over Wi-Fi. And a lot of the Wi-Fi NIC cards don't include the PXE bootloader. So not something you'll see a lot of. I'm happy to talk about it if you want to. Same thing with VLANs. We're talking about systems that really aren't that configured. So you could do VLAN, but usually we're just on the naked network because the systems aren't there yet. And then they move off of VLANs really quickly. Containerizing, people love putting everything in containers. You can containerize this. About half of our customer base runs digital rebar in a container, and that's fine. It's okay with us. It's not our preference because you're talking about UDP. DHCP is UDP, TFTP is UDP. And so you're going to have to probe things through your containers. We can help you do that, but it makes things harder. So it's one of those few places where containerizing isn't an automatic win. BIOS and RAID, very important things. None of what we're showing you actually sets BIOS and RAID. They're very sensitive to BIOS and RAID being correctly configured, and you need to be careful about that. That is a whole nother series of talks, and something we spend a lot of time helping people do. PXE does not solve that problem for you. So you need to get your systems configured as part of this process. And then how do I make this faster, right? Things I showed you can take some time. And that we're going to cover in some more detail. So before we talk about making things faster, let's talk about simplifying. So one of the biggest ways that we simplify this whole process is we have an in-memory operating system called Sledgehammer. It's based on CentOS, and it is RAM only. So it doesn't rely on very much information about the drive layouts or anything like that. And we have been pounding on this operating system install for almost a decade. It's very small footprint. It's just enough to OS, and it runs on pretty much every platform imaginable. And so we use that to boot and then run a system. We do an inventory and a scan of that system. That information from that inventory then informs what we do next. So the idea here is that we're doing a quick boot in a system where we have control, where we can collect a lot of data, and then that gets fed into the templates in the next phase. The more information you have about your systems, the easier the downstream processes become. And because Sledgehammer has so few dependencies on the physical systems, it allows us to get something up and moving really quickly. I strongly recommend this. We've seen this pattern is getting implemented pretty widely as a discovery OS or boot OS. It's really powerful. We use Sledgehammer for all sorts of things, from RAID and BIOS configuration to image deploy and things like that. So that's really important. And image deploy is our recommended way to get systems going. So image deployment is different than PXE. As a matter of fact, it gets you out of the whole PXE process, and it can be a really, really good way to speed up and make more resilient and secure all of your infrastructure. So let me explain how this works. If you start with this in-memory OS, you get a very small footprint. You have a place you can do work from. Inside of that OS, you can actually download a disk image compressed. The more you can compress it, the better. Usually generated as like a tar out of something like Packer or a cloud, ONIE or VMware image, something like that. You take an image of that disk, you download it into that system, and you write it to the drives. You fix the disk partitions so that you can boot it. So you have to have a boot partition written to the disk. You actually write the disk, you build the partitions. There's actually a lot of work that happens here. It's not as simple as just dropping bits on a disk. You actually have to build a partition table and set things to boot, set everything correctly. So there's a little bit of magic that gets done. And then you reboot the system. When you reboot the system, now you've got that standard image base baked into it, boots right up. It starts that. Then that will use some machine initialization code to actually do the post configuration that you would normally have done at the end of a scripted kickstart type install. So you still need a cloud init or a machine init process. You have to serve those files. You have to start something inside that image. And frankly, when we're helping people do this, laying down the image is really not that hard. This part of the process is easy. The thing that really trips people up is building a good image. And I have whole hour talks about what image-based deployment processes do. But the thing to keep in mind is that golden image, that deployment master, that will be have to include enough to get the hardware identified, the drivers that you need, some base information of where to go to pull down the additional configuration. So it takes people some time to get that right. The other thing that you can do that really speeds things up is to do immutable provisioning. CoreOS made this sort of famous. There was a Docker OS. Rancher has K3 OS, or they're used to have Rancher OS based on Docker. Obviously, a lot of people thinking about this from a Docker perspective. For us, we have a in-memory OS, and we can do immutable provisioning based on that. We do all the time. It's super handy. But the idea here is that I start that image, I attach and I configure and attach the system as much as I need to. So I've initialized the machine, so a cloud init or a machine initialized, and then I start loading apps or containers. So I'm going to go to my container registry. I'll just start Kubernetes or some other container scheduler and start making those things go. The catch here, and this is really important to consider, is if you follow this model, it's easy in cloud where your virtualization infrastructure is taking care of things. On Metal, you better have a highly available provisioning service, because every time your server boots, it's going to have to go through this provisioning cycle. It doesn't write a disk partition. It's always going to be going through that. And it's a value in the process, but it does create a weak point in your provisioning service. A lot of the open or older provisioning systems have no concepts of high availability. DHCP is not by default a highly available infrastructure. And so this does create stress on your environment. It has some benefits too. And you thought we were doing the advanced stuff. We've only touched the surface on provisioning. So let's dive into some advanced topics beyond this, things that really are a little bit more esoteric or specialized. First one on my list is ESXi VMware provisioning. There's a lot of VMware out there. There's a lot of people deploying VMware, and the fact that it's tricky keeps people from doing it themselves, and they end up buying very expensive hyperconverged solutions or incredibly expensive appliance type solutions for VMware. We've been doing a lot of work to just script this out. When you have all the provisioning automation as infrastructure as code, it becomes much more possible and achievable by humans and repeatable by people by following some simple steps. In ESXi, their bootloader is called Weasel. Same as like a Kickstart, you pass in configuration templates. That allows you to then move to the next step. The VMware kernel ESXi kernel is very restricted. So you can't really do a lot and run a lot of utilities in there, but you can run some Python scripts and code. We actually have a version of our agent that starts and stays in that mode. We worked with VMware to get it secured so we can start doing scripts. It's still a restricted environment, but that post configuration is really important because you need access to the system. You have to have your APIs, security, passwords, ideally your TLS, your name, your IP set, all these things have to be done. Some of it's done in Weasel, some of it you can't do in Weasel because Weasel's a restricted configuration language. Once all that's done, ESXi is ready to rock and roll, and then you are, bless your heart, using VMware tooling to do the rest of that configuration. And there's actually multiple types of tooling to make that happen. But this is the normal flow. All of this can be codified. It's all APIs, and you can make it work. It just takes some more magic, and you have to work around the restrictions or the tooling that's available. Another thing people get interested in is ONIE, Open Network Install Environment. This is really something that we saw a couple years ago. It does get used in Open Compute. It's really for switches, and it's different than PXE boot environment that I've been describing. It's really a firmware imaging process. So in an ONIE boot, it's going to do the same type of DHCP, but instead of doing this sort of bootloader approach where you're going to build up a kernel, what it's going to do is it's going to download a new firmware image, really an OS image for the whole system. It's going to take that OS image, write it into the firmware, and then boot into that new firmware. So what you're really doing is swapping firmware in and out. Edge devices have a very similar concept because they're all firmware devices. The idea that I could in-memory boot an OS and run the kernel in the switch is really not how switches operate. They don't have that type of storage design. So ONIE boot, while it's really interesting for these, place a lot of restrictions on how you're going to run the system because that firmware image has to have everything baked into it that you're going to need. So it's hardware specific. It's really design limited. They do have DHCP options to run a startup script. And so you can embed, hey, start the script after you've started the switch. And that's really handy to like start. You can run an agent in there or a script or start some process or program. But once again, very, very limited compared to the other processes that we've worked out. The next thing on this list is kernel exec. I'm a huge fan of kernel exec. It's really cool, and I wish it was more commonly implemented so that we could use it more. Kernel exec is actually what's happening behind the scenes all the time when you reboot your kernel. What is actually happening is we're starting with a running OS, and that OS could be one of the bootloaders. We download a new kernel, and then we exec the kernel. So we transfer the operations of the operating system into a new running location. So it's a reboot, but without rebooting. We're just changing out the kernel, and then that does a start. And this is amazingly powerful. This means that we can transition between operating systems without going through a whole reboot. One of the things that takes a lot of time in this process is that if you reboot the system and go back through the PXE process, you're doing what we call posting the OS or posting the hardware, which means it has to go through that whole BIOS startup screen and figure everything out. You can spend 10 minutes, big systems, big data center class servers can spend 10 minutes going through that BIOS system before they even start. That actually causes all sorts of problems in DHCP servers where they can lose leases and change IP addresses. It's a mess. But this eliminates that. And so you can jump literally into a new kernel. Sledgehammer does support kexec. So we have some fun times where you're running in an OS, really any Linux, you've enabled kexec changes, and you can start Sledgehammer just by jumping right into that new OS. Super powerful from that perspective. And that would look like this. You can come in, you can just switch the OS. RI-PXE infrastructure can also be kexec. So even if you have an operating system like Ubuntu that doesn't support kexec in a standard way for us to link into, you can still skip the reboot by starting the iPXE process through kexec and then jumping right into the netboot process and eliminating the whole PXE process where you have to post the machine and get to PXE, download the bootloaders and things like that. You can just drop straight into that process. And that can save a lot of time. So in this case, you could go from one OS, kexec into Sledgehammer, very quickly get that system running, then kexec into your next system install. No reboots at all, just image. It's really, really powerful way to speed up your whole process. And that's why it's so important to list it here. Although not every operating system can support it. If you're in a CentOS Red Hat world, definitely if you're in an Ubuntu world, sort of, and then your mileage may vary after that. A lot of people are really interested in Secure Boot. If you're not using Secure Boot, please look into this. This is something that everybody should be doing. Every common server today has trusted platform modules, or TPMs. The TPMs have keys in them that allow your server, when it's enabled to do this, to reject unsigned operating system components and basically stop working if they're not using a trusted system. Now, that does nothing to protect you from somebody logging into your operating system and installing malware or something bad or misconfiguring it. It doesn't help you there. But it does ensure that at least through this process, you are using trusted firmware the whole time. The challenge here is that for you to do Secure Boot, once you've enabled it, every step of this PXE process, remember how many different OS installs it is, has to be using a signed and secured process. That means your first bootloader has to be a signed bootloader, and your second bootloader has to be an assigned bootloader, and your first kernel has to be a signed kernel. And you can't just, or it's not easy to sign your own systems. You're actually, you're using keys that are injected in the TPM at the manufacturing floor. So typically these mean that you're using a trusted OS from one of the vendors who have keys that are already in the TPM, and walking through that process. And that adds some complexity and overhead, and you have to be able to run this process in specific ways. We actually spent a lot of time making sure that we had all the bits and bobs right. From, say, via VMware Sense, that also means that all of the modules that you load into VMware also have to be trusted. So they have to be trusted kernel components as well and signed. And so if all that stuff doesn't match up, then the systems won't actually load. And that is a problem. That means once you turn on secured firmware, you better be able to take the process through all of these steps, or it will not boot. And you will be stuck basically with a server you're going to have to physically touch to flip its BIOS back to insecure so that you can go through a standard boot process. Yeah, it takes, you have to get this right, and you have to have a lot of confidence. I can't stress it enough, a lot of confidence in your provisioning service. If you're like, it's going to work, I'm going to squint at it, and if it's, the moon is in the right phase, it's going to work, Secure Boot's probably not for you. You need to be really confident that you've got all this stuff working, reliable, and trusted. But you should do it nonetheless. The other one, the last one here is more esoteric. We see people asking for this all the time. We prototype it for people all the time, and then they pull back from the brink on this. Most modern BMC, baseboard management control systems, IPMI, out-of-band control, have the ability to add install media into the system. So you can upload an ISO and tell that out-of-band management controller, hey, I want you to boot this as if it was like a USB installed on the system. Once you do that, you're into an attached OS install mode. It's just like a USB stick. That goes through a kickstart process. You're going to have to preset the kickstarts so that you can do that process. That doesn't save you from the normal installation process. So once you get Kickstart rolling, most OS, unless you've tuned it, are going to still go through the downloads, are still going to need post-config. You're going to have to go through all this process, or you're going to be building very customized install media that does all this for you. That's why it's not that popular of an option. Once you start thinking about what you have to maintain and build from an install media perspective, this becomes sort of untenable. What we've helped people do is come up with a hybrid. So instead of having to take a full install media, what we can do is we can make our bootloader into a attached media device. That eliminates the DHCP. It can eliminate DHCP. Ideally, you don't. DHCP provides a useful ability to create automatic reference. But what it will do is it will jump straight to the bootloader. That bootloader can then pull down the kickstart and the templates and all those things. And so that then eliminates the PXE process in these systems. And it can speed things up a bit. But once you've gotten to this point, I'll tell you, we've optimized the bootloaders so much in this process, it really doesn't take a lot of overhead, and the value that you get for locking in the server like this is really minimized once you get all the way through it. So, but people ask all the time, so I wanted to include it in this presentation. And that is the presentation. My name is Rob Hirschfeld. I'm Zehicle Online if you have questions. We do this for people all the time. Digital Rebar, which is our product, it's free to try and download. It's behind the firewall, soft service, infrastructure as code provisioning. Please check it out. Even if you just want to go and look at how we've done our Kickstart and pre-seed files, there's a huge amount of institutional knowledge baked into this. And really, you don't want to be figuring this out yourself. There's no business value or education value in becoming the master of Kickstarts at your company. You really want to be working up stack and figuring out how to make this repeatable, scalable, faster, and secure. So please check this out. I'm around for questions. I hope you enjoyed the talk, and I will see you at our booth at SREcon 2020. Thank you. Oh, good. You're still here. Almost forgot. I wanted to tell you something about Raspberry Pis and PXE booting Raspberry Pis, because that is a bizarre topic, and I promised I'd say something about it. We've been working on something called edgelab.digital, which is a Raspberry Pi automation environment under $500. It uses Digital Rebar, so it could actually boot anything, but we figured out how to make PXE booting Raspberry Pis simple and repeatable. There is firmware for the Pis that you can use that will let them be PXE booted, but like I was saying, protocols for PXE are variant, and so to make it work, it's not quite what you would expect. So we've built this into Digital Rebar. You could replicate this with your own PXE server. In our subnets definition, we build one for EdgeLab. It builds it automatically, but you actually have to include additional options in the system that translate into a string that tells it where to find the proper PXE boot files. That in itself is not enough. There actually is a drop-through chain of file resolutions that need to be included. And so when we built our Sledgehammer install, which is what gets going, there's actually a Raspberry Pi variant set. You'll see at RPi, where we have a hacked up version of Sledgehammer that uses kernels that work on the Pi, and then have the additional image deployments and options for making Raspberry Pi PXE boot work. It does work. You can Sledgehammer boot, PXE boot, immutable memory boot Raspberry Pis. It is reliable. It is a great way to run Pis. It reduces wear and updates of your SD cards, and I strongly recommend checking it out. If you use Pis, it will save you a lot of heartburn and time. Hope this extra segment was helpful. Thanks.